All right, so if we put all that together and come back to our Kobe plot that we were looking at before. So again, here are our regions. Keep in mind biomass along the bottom. This is good, this is bad. Fishing mortality versus, so this is now as a rate, fishing mortality versus natural mortality. Here's our 1-to-1 ratio. Our fishing mortality is currently almost 2 times higher than it should be, both across the whole state, but particularly the southeast. The southeast is our worst hit. So we are, and our biomass is below 20%. Now it's about 18%. So we've moved from over here, whoops, we've moved from over here now into the depleted state. So where we want to get us is back down here, back across here, and then reassess what we would do with, you know, the management of the fishery. So we just need to get that bigger biomass in. So that's the challenge now, is how you convert this science information into a management strategy that will provide, you know, a fishery that's of value to the recreational fishing community. Because again, this is one of the opportunities we have with this fishery, is that because it is predominantly rec fishers, you know, there are ways that we can get bigger fish into the biomass, protect them, and then potentially relax that protection for the bigger fish, so we can have maybe less fish taken, but there will be bigger ones available more, or a whole range of methods. I'll just do 2 more hooch, and then I'll take the question, because these are the ones that to me really clearly show it. So now there's a question in there about, you know, is this based on numbers or biomass? So what this graph here is showing, is, again, we've got the size classes along the bottom. This is in the southeast of the state. It is just females. Red is the size composition that we are seeing in our 5,200 samples we've taken over the last period of time. Green and blue are model estimates of what the relative numbers would look like without fishing, okay? So now the difference, and this is of mature fish. So again, keep in mind, we were talking before that one of the biological parameters we get is size at maturity, and that's most often looked at as size at 50% maturity. So that means 50% of fish of a length of, let's say, 22 centimetres are going to be mature. So there'll be some at that size that aren't, and some at that size that are. So that's why, you know, this drops away down here, because these fish are now just not mature at all below 16 centimetres. If this was on true numbers, and as we said, you know, we were just looking at all numbers, these would go through the roof down here, because obviously, you know, there's lots and lots of babies out there, lots of juveniles, and fish have fairly high natural mortality rates because there's lots of predation and so on. But this is just showing mature fish that are unfished. And then the green ones, the difference there is there's a selectivity factor in that. So we know that, you know, you can catch small flathead, but with the methods that we're using, we're seeing that there is a selectivity effect where the hooks aren't catching the really, really small fish. Now, so that's that side. And this is where it gets interesting, is by number, when we're around that size limit, you know, we're not far off what we would expect to be seeing, you know, around once we start to, you know, just below the size limit. But as soon as we get towards the size limit, that number drops off dramatically. So this is kind of what we've lost from the fishery around the state, is this, you know, this area here. So green basically equals blue once you go down here, because they're all selected to the fishery. They're all, you know, can be caught by the same hook. So that doesn't look great, but, you know, around the size limit, yeah, we can probably keep fishing, and, you know, we can catch fish. They're going to be small. If we look at it in terms of biomass, now this is where the problem comes in, because bigger fish weigh a lot more. They contribute disproportionately to the eggs, but they are also what is the main abundance in the biomass. They contribute a lot more by weight. So an individual fish contributes a lot more by weight when it's longer. So this is now what we've lost, and this is the problem we've got. So not only are we changing what the fishery looks like, we're putting the biomass in a state where, at the moment, and we'll come to this, recruitment isn't, we're seeing relatively stable recruitment. but it's fluctuating, and we expect there's an effect. But if there was some other, there's a question about climate change in the comments. If there was something else that started to affect the recruitment success of these fish, it's pretty much the only thing they've got going for them is they produce a lot of eggs and they seem to have fairly good survival. That's why we've got the numbers coming through. But if there is any risk or a year that something happened, a big freshwater event or something that affected recruitment greatly, we are in a very bad way. We are right on the edge of collapsing this fishery if recruitment becomes impaired, because we have removed a lot of biomass. Just to really quickly show, this is a simulation, basically age versus biomass, and someone talked about, with effort going down or catch going down, how do we still have an effect? How is it still having an effect? So it's a cumulative issue. James, do you want to talk through this one while
you can. You've seen it, so yeah.
Okay, I just needed a drink of water.
All right.
But basically, that first step of fishing, you're taking out a big chunk of biomass, but it's cumulative in terms of the impact. So you are moving closer and closer, to depleted state when you start fishing.
I think if you can just go back up, Sean, as well, the big critical point here is that if with no fishing, and then the first little increment, which is not even half of natural death, about 30% of the biomass gets removed because you're removing all those large fish. And then with the next little bit of fishing, it drops to about 57 or something like that. But even when we have really heavy fishing, little bag limit moves from, don't actually have that much of an impact on the biomass.
Yeah.
If you flick between those two, they really, it's not doing much. Yeah.
And then the last one, so we talked about recruitment variability, and this is, again, are there things that are impacting the, survival of eggs and survival of recruits, aquaculture, seismic testing, a whole range of other things, and we will touch on these in a little bit more depth. But this is how we sort of assess the consistency here is, these are the age classes. So we saw the otoliths before and how we age a fish, and you can basically go, all right, well, you were born 7 years ago, so your birth year was whatever, and back to here. We take out the middle ranges because these fish here are now starting to die out of the population, whether it's natural or fishing, so we don't necessarily include those. And these guys here aren't necessarily potentially fully recruited to the fishery, as in are going to be caught. But if we look in between these bars, for a 5-year period, the recruitment, so this is the number being born in each year, is reasonably consistent in most areas. And I say reasonably, like there is variability, but you compare this to a reef species or snapper or some of the issues they've got on the mainland with the WA reef fish that are highly variable. That's why they're got big problems as well, because the recruitment isn't on their side. At the moment, we're doing okay with recruitment, but it is really on the cusp of starting to see some effect in recruitment because of that loss of biomass.